Howdy, it's Mr. Russell, and we're going to continue Chapter 1 by reviewing the SI system. Know those prefixes on blue on page 10, and it's also important to know the difference between mass and weight. The mass is how much matter an object has, and the weight is the pull of gravity. So the mass is, we can interchange those usually, but we do need to know a difference. So the pen here has matter, and so it has mass. If it was taken to the planet Mars or Pluto or maybe the moon, it's not a planet, and it would have the exact same amount of mass. Okay, but it would not have the same weight. The weight, because the pull of gravity is different on all those different places. These are the tables that I was just referring to in the previous slide on page 10, where there are 7 fundamental SI units that we'll be using in our chemistry. Actually, we won't use a couple of them. We won't use ampere or candela. Those physics terms, and we won't use them. And every other unit can be based on or derived back to this unit, like the joule and stuff like that, are based off of some combination of these. These down here are the prefixes that you have learned most of them. You've heard King Henry died drinking chocolate milk. Have you ever heard that before? And you're probably familiar with the term mega, giga, and tera, just based off of a gigabyte or a megabyte, right? But did you know that it goes farther? And this is how far it goes. And it can actually get smaller than milli. It can go to micro, which will be used, nano, pico, femto, and atto. Only the ones in blue are the ones you should be familiar with, so come back to this later if you need to. We'll have to start taking account for all the uncertainty that's in our measurements. In every measurement should always include a certain digits plus the first uncertain digit. Remember that every instrument will have some kind of uncertainty somewhere, even the most precise. On a digital device, the last digit shown is uncertain. So on a scale, even though I have 4 decimal places there, that last one is actually uncertain. What would be the reading from this graduated cylinder, and how many decimals are acceptable? The reading should actually be 52.8. Notice that you could see 52 from the lines. You need to be able to approximate that last actual extra digit. Get in the habit of adding that one last one, because the human eye can approximate to a reasonable degree of error, to about a tenth of this place. Okay, so go ahead and just add one more digit to your best judgment. The purpose of this is so that you would know that this is closer to 53 than it is to 52. We're going to have to know and use these 4 pieces of equipment, 4 pieces of glassware. The first one is the graduated cylinder. You're familiar with it. Not very accurate. Not really even very close. It's got I think it's a plus or minus 5 milliliters on that. There's not very accurate. There's a pipette. The ones that I've been using, the little plastic ones, are about 3 milliliters. This one's a 25, so they do get bigger, but the reason why is because they're glass and they break. So let's just not use. We probably won't use these too much. There's a 50 milliliter burette. Notice that this little break right here means that this is actually much taller than it should be, than it looks. This is the most accurate and most precise piece of glassware you will ever see, most likely, because these burettes are expensive and very, very, very nice. I'll show you how to use those later. And you've probably seen me use these before, the volumetric flask. They put all of their effort into drawing one line. This line is exactly 250 milliliters for a 250 milliliter volumetric flask. You can buy bigger ones or smaller ones if you need to. You'll get a chance to use those. You heard me use the term accuracy and precision. What do you know what they mean? This one is not accurate and not precise at all, because none of the darts are close to each other or close to the bullseye. These are close together but not close to the bullseye, so these are precise. They're close together. But it is not accurate because they're not on the bullseye. So to fix that, you could either move the darts to the bullseye or move the bullseye to the darts. That would be the chemistry equivalent of calibrating your instrument. If you know that it's calibrating down and say your pH is always reading at 6.5 when it should be reading 7, you can recalibrate it so it bumps it back up to 7, or you move that target. This one down here is accurate and precise since all the darts are at the bullseye and close together. We keep track of these in our numbers by using sig figs. How many sig figs are here? There are 5 here because any non-zero number is significant, and any number between any zero between two significant figures is also significant. That's that sandwich rule. So 1, 2, 3, 4, 5. Now for this one, there are 3 sig figs. The first, if a decimal is present after the first non-zero number, every number after it is significant. So it doesn't matter how far this goes, every number after this is significant. Here we have a decimal present and a non-zero number, so every number after this is significant, but a leading zero is never ever significant. So these in the red are not significant. These are. Here, these are not significant because they're leading zeros, and these are not significant. So, but these are. In our calculations, we'll have to remember a couple rules. When you multiply and divide, you want to use the smallest total number of sig figs. So if there's 2 sig figs here and 3 sig figs here, your answer should have the least number of sig figs, which is 2. So your answer has 2. But if you are adding and subtracting, you need to use the least number of decimal places. You want to keep those decimal places. Okay? Exact numbers have an infinite number of sig figs, which means they just don't count and we don't take them into account as the least number of sig figs. So if something like if you're converting meters to kilometers, there are 1,000 meters in a kilometer, exactly 1,000. So we just don't count that 1,000 as part of our multiplication rule. That's what it's saying. If you get an answer like 600 or 400 or something like that, you want to show 3 sig figs though, the best way to do that is to just put it in scientific notation to get around it. Remember, anything to the left of the multiplication sign is significant. So now it's easy to see that this has 3 sig figs. You could also put a decimal place at the end. That way a decimal is present, and so after the first non-zero number, everything is significant. That's another way to get around it. And because this is a chemistry class, you will have to use dimensional analysis. There's no way to get around it. And those conversions are going to be found in the back of your textbook for your bookwork problems. If the AP test gives you something, they will give you the conversions you need. I guarantee it 100%. In our lab, we'll never use Fahrenheit. We'll always use Celsius and Kelvin. And it's important to try to commit to memory that 0 degrees Celsius is 273.15 Kelvin. The 0.15 is not super important for you to memorize, but please remember it's 273. It does not show you on the formula chart this part right here, but it does show you what the temperature is at STP, which is this temperature here. So that they sort of show you. We'll have to remember our units for density as well. Remember, it's mass over volume. So, and for solids, it's grams over centimeters cubed, or liquids. But for gases, it's grams over liters. Centimeters cubed and liters are the exact same thing. Did you know that? Yes, but for gases, since we use liters so much, grams over liters is necessary. Please make sure you know this, how to classify your matter. And if you need extra help, refer back to the first year videos that I have already made this one. So I know it's there. Go ahead and ask me and you can find it. I'll show you in more detail. Be familiar with the physical and chemical changes too, because they will be there. It's important for you to be able to identify them and know what's happening. If there's chemical changes going on, obviously there's going to be clues that you need to look for. And remember that they can be both. Something like dissolving salt and water can actually be both a change, because you're separating the molecules and rearranging them, but you are also chemically changing them as well. The weak bonds in between the water molecules and the salt. Here's a great picture of it where the calcium and the water molecule are now weakly bonded, so that would indicate a chemical change. I've also made a video on this, so I'll move on it briefly, with distillation, chromatography, and filtration. This was a distillation apparatus where you can separate two homogeneous liquids. But it looks cool, but it's pretty hard to pull off in the lab, and there's a lot of errors involved. We'll have to use these in filtration, where we're gonna you use this in first year chemistry and gravity filtration, but now you'll get to use vacuum filtration. I have some vacuums where you will get to basically pull the liquid out of the solid using a vacuum. It's a pretty cool thing. I'll show you how to do it later. The chromatography, I will show you how to do that as well, using paper chromatography to basically separate mixtures based on their polarity and how they like to attract to other molecules. So this would be an example. If you had a Sharpie, you could actually separate them based on just their attraction to the solvent. As the solvent travels up the strip, it's actually going to pull those molecules away and separate them in different areas. You can then measure the length to find out the amount and the concentrations of them. And that is going to be it. Thank y'all.